morning. Welcome to Technical Insights 1. My name is Chris Dick from Xilinx. I'm very pleased to be the moderator for this session. We've got a number of very interesting papers on the agenda, starting with Cormac Brick. Cormac Brick is the Director of Machine Intelligence in the Movidius group at Intel Corporation, where he builds new foundational algorithms for computer vision and machine intelligence to enhance the Myriad VPU product family. Cormac contributes to internal architecture and helps customers build products using the very latest techniques in deep learning and embedded vision through a set of advanced applications and libraries. Cormac has worked with Movidius since its early days and has contributed heavily towards the design of the ISA, hardware systems design, and computer vision software development and tools. Cormac has a BEng in electronic engineering from University College Cork. So I'll hand it over to you, Cormac.
Hey, thank you. And thanks to the earlier speakers as well for their excellent talks. So I'm here today to talk about the battle between traditional algorithms and deep learning, 3-year time horizon. I think this should be of interest to people who are interested in working on algorithms, but also are interested in building hardware platforms that are going to be relevant for the next number of years. I think looking at workloads is very important in that context. Yeah. So who are we? At Movidius, we have been, active in a number of markets. We have shipped a lot of products in the last year around security, where we've been particularly used to bring kind of deep learning to those platforms. We're very active in the drone space as well. We've also done a lot of work in kind of AR and VR, and increasingly we're doing a lot of work on kind of service robotics. Kind of me personally, I've been engaged with a lot of these customers, and also are engaged a lot around kind of hardware architecture and algorithms looking forward at Movidius to kind of see, hey, what's going to be the best balance of compute that will best serve these types of markets and the customers we're working with today over the next number of years. Okay, so the battle. If we want to think about there being kind of two buckets or kind of two camps, one is kind of classical computer vision that's used today for lots of things. So examples of kind of algorithms in that bucket today would be things like kind of human engineered feature descriptors, things like kind of SVM, where perhaps kind of shallow learning is used, and any kind of DSP techniques like kind of bilateral filters or Hopf transforms or any kind of classical algorithm that doesn't use kind of deep learning would fit there. And then deep learning, I guess there's any number of sessions on that at the conference this week. So there's any number of techniques as mentioned on the right. But really what would kind of differentiate them is they're both deep. So they may involve kind of learning many different layers. And typically the parameters and increasingly the structures of those solutions are learned through backpropagation or reinforcement learning. Or evolutionary techniques, as opposed to something that a human decided, like, hey, it's good to have an oriented gradient or a histogram of oriented gradients, for example. And why is this an interesting problem to look at? So if we look at any one kind of algorithm vertical, as we want to kind of build new experiences and build better products, one of the questions we kind of want to look at today in this session is which techniques are going to dominate in different algorithm verticals. So an algorithm vertical for me would be things like kind of stereo depth is something we're going to look at. SLAM is something we'll look at. Things like kind of gesture recognition or or image classification or identification. These would be examples of algorithm verticals. And why it's interesting to look at this question is purely from an algorithmic point of view. It's always interesting. But if we want to have If you're here kind of thinking about defining an engineering platform that is going to be relevant in 3 to 4 years' time, you will want that engineering platform to be able to perform very, very well on the compute workloads that are going to dominate. And as many workloads move from classical computer vision to deep learning, it's an interesting question to ask us, where do we think we're going to end up in 3 years' time? Because that balance is probably heavily towards classical computer vision and shipping products today. But in 3 years' time, we'll expect it to be in a different place. And that's what I want to look at today. Okay. So first, just as a bit of kind of scene setting, we might take a look at where we were 3 years ago. Then look at what's happening today, both in theory, in terms of what's happening in published work, what's happening in the real world. Then maybe quickly look at why there is a gap between what people are able to show in theory and what people are shipping in the real world today. And then look at some of the trends that are going to impact what's going to ship in 2020. Okay, so 2014. So looking back at the Embedded Vision Summit archives, like I and probably many people here were at Embedded Vision Summit in 2014. And that year, kind of Jeff had the foresight to invite Jan LeCun around, and he gave an excellent keynote on convolutional neural networks. But apart from that one keynote, which was really looking ahead, most of the other talks 3 years ago were discussing classical techniques, and to the best of my knowledge, only one of the talks specifically mentioned deep learning as a technique that was seen as relevant. And what sort of things could we do 3 years ago? So deep learning gave very strong results on full image classification, as was seen by ImageNet for a couple of years at that point. And another interesting result we had 3 years ago was the portability of extracted features. So you could train a network on one data set and then train the last layers to solve a different problem. So, popular things 3 years ago would have been being able to show the flower classification problem was one where transfer learning was shown to work really well. Also 3 years ago, we had good results in speech. But beyond that, we couldn't do fully convolutional localization. So this is locating an object of interest as opposed to the type of object in an individual frame. And there's lots and lots of other things that we couldn't really do using deep learning techniques. So even then, it was deep learning was seen as something that gave super strong results in image classification. To be effective, you had to pair it with classical algorithms, such as something like edge boxes or a region proposal algorithm had to be paired with that to be useful in real life. And it was unclear to what extent, even though there was a lot of promising signs, it was unclear to what extent deep learning was going to be able to take over new application domains. Okay, so where are we today? Where we are today in the surveillance market is, lots of our customers and just lots of companies in general who aren't working with us directly are using deep learning and surveillance, really capitalizing on what we knew 3 years ago, that deep learning is now able to do improved accuracy on image detection. These days, people would be using something fully convolutional to do the bounding boxes, as well as telling you what's inside a bounding box. So things like fast or CNN, YOLO, and other such techniques would be used for region proposals, combined with something that is telling you exactly the nature of what's in each of the bounding boxes. There's increasingly fully convolutional networks can do that in a single pass. So there's a lot of work being published this year at CVPR and elsewhere showing how we can now do region proposals and detection in a single pass with state-of-the-art accuracy. Okay, so next I'd like to look into two technical things that maybe my team are looking at a little bit to give a bit more direct insight in a little bit of depth at how deep learning is affecting other real pipelines we deal with and ship in the real world. So here, what we're showing here is 3 ways of implementing stereo depth. And today is the classical form, where you would have some form of transform, where a lot of people would use senses or variants thereof. We'd have some sort of compute that would be used to compute the cost vector. Then there would be classical techniques used for cost aggregation. So examples here would be, in the embedded world, this would be predominantly semi-global block matching, which I think Mark mentioned that they use earlier. They use SGBM type techniques in their depth. And would then have some sort of post-processing. And on the right is the example of the type of result that sort of approach can give you. These days, a lot of teams are looking at using deep learning, either before or after cost aggregation, where it's pretty straightforward now to use, instead of using a human-engineered transform, like the census transform, which is which is a very neat way of kind of representing the world, but is ultimately a kind of a human-designed way of representing the world. We can now use deep learning approaches to either just learn the transform or learn both the transform and the cost compute part. And that can give us the sort of technique as kind of seen on the right. And there's a couple of references there that are in the slide material you can also look at for examples of exactly this technique. And so I would say kind of today, somewhere between the first and the second line represents the state of the art of what's shipping. If I look at kind of published work, really just in the last couple of months, there's been a few things published, both in January, and there was a paper published in February by the SkyDIO team, who are kind of a team based in Silicon Valley who do a lot of work on drones, and they've managed to obviate the need for kind of classical cost aggregation and have a fully convolutional technique. And that's very promising. It is, some of that is quite complex, both in terms of the theory and in terms of the runtime of the overall system. But yeah, here I guess the bigger picture is, I think that these is like one of the reasons why SGBM has been a harder thing to displace is it is effectively belief propagation, and it relies on a good knowledge of the geometry of the scene and some of the implicit assumptions are kind of used in designing that belief propagation algorithm, which has been why it's been a relatively hard thing to displace and has been a hard thing to directly learn those type of geometry considerations. Okay, so to briefly then look at another technique and another kind of algorithm vertical, and this is kind of using the same color scheme as was previously. If we look at any SLAM system, we'll typically have these kind of 5 major components where we will look at a scene, we will do some tracking based on 1 or more cameras, we will do pose and sensor fusion from 1 or more cameras, typically plus an IMU. Then there'll be some local mapping and optimization, where we try to learn a consistent view of the world. There as well, we'll do something like on a loop closure, where we want to say, hey, or am I in the same place as I was sometime in the past? And another component then is we would do kind of global or dense mapping, where we would use where we want to kind of build a longer-term consistent view of the world. So the local map that was in the earlier box and this one may be different things, or they may be refined versions of the same thing. So today, classical techniques, and if you listened to, I guess, to Mark's talk earlier, he was kind of describing a PTAM type architecture, which itself is kind of based on kind of a family of algorithms, and ORB-SLAM would be a very particular kind of popular example of one of those algorithms. So ORB-SLAM today uses kind of ORB features, so oriented brief, as the kind of the features that are used for tracking. We then tend to use EKF for sensor fusion, and then we'd use kind of classical nonlinear optimization techniques for local mapping, and use bag of words for loop closure. And the global dense mapping there's a number of techniques largely based on global optimization that would be used there. So today people are enhancing these pipelines using deep learning in a few ways, and there's also some efforts to try to displace the full pipeline with deep learning. Today, the enhancing has yielded kind of better results. So examples there would be if you have a monocular system, people would enhance the depth problem, or the depth initialization problem that Mark referred to earlier in his talk, by using a single frame depth estimate is very useful to kind of there's a particular initialization problem in sensor fusion, and using a network that can learn a version of depth from a single frame is very useful there. Other areas where people would use deep learning today is there's another kind of map consistency problem. As you try to build a map that is consistent over a very long time, one of the things you can do is you can learn imagine you're a car driving down the street, and if you see that there's a kind of a car parked at the side of the road, that will be there today, but it's probably not going to be there tomorrow or the day after. So even though it's a good thing to use in a local map now, it's not a good thing to add to your global map. And you'll end up, so we can save a lot of optimization cycles by kind of adding a kind of a 2-state classifier, or adding some sort of semantic knowledge to as an additional input into local mapping. So we can say, hey, that's a car, so I can use it for pose estimation now, but let's not add that to the global map, because it's probably not going to be there all of the time. So that way, if we want to maintain globally consistent maps over a long time, semantic knowledge of the scene is a very, very helpful thing to have, and deep learning can play a big role there. Going beyond that, there's a couple of kind of papers published out of kind of Google and Berkeley in the last couple of months, which are doing kind of, there's a SegNet, and there's also something else doing, or SFMNet, and there's other work kind of showing unsupervised deep learning to do end-to-end deep learning to obviate the need of these particular steps. But I would say that work is still quite far out today. And today what's mainly shipping is variants of, certainly in people who are doing feature tracking-based SLAM, variants of these techniques are kind of what are largely shipping today. One thing that is worth mentioning is around kind of loop closure, is because we can use CNN for image detection, it does have a role to play in kind of loop closure as well, and that's another area where people have embellished a classical architecture using deep learning techniques. And one other thing probably mentioning on SLAM just before moving on is SLAM is very useful for robotics and for AR and VR. If we look at things like the Amazon Pick Challenge, today people are where that challenge is where a robot tries to pick an object off its shelf and put it in a basket. There, a lot of the existing and older techniques of that would involve building a dense 3D view of the world and then using that to kind of manipulate the robot arm. Today, particularly for robotics type use cases, having reinforcement learning as part of what the robotic arm does can obviate the need to have a full 3D view of the world in the first place for the robot, for that particular task. Yeah. So in summary on SLAM, there's certainly looking back to Mark's talk this morning, people can ship perfectly good systems using just classical techniques alone. Today, a lot of people are embellishing classical techniques using deep learning techniques to build incrementally better versions of the architectures they're working with today. And while there is some work on fully end-to-end deep learning in this area, it's a little way off yet in terms of being deployed in the real world. So common themes. So if we look at what the cases where today deep learning is used a lot versus places where classical techniques are used a lot, these are some of the common themes that can emerge. One is features are easy. So for image classification, learning feature embeddings either via supervised or unsupervised techniques are very easy, and that's something I guess we all already know from kind of the history of ImageNet. Pixels are possible, is what I would say there. So if we want to, even though I haven't looked at it in the last two slides, thanks to the advances in generative techniques, like generative adversarial networks in particular, over the last 12 months, we can now train much better kind of image denoising filters, or in the depth pipeline for that post-processing block, we can use generative techniques there to generate a better version of depth in the output. So today, thanks to advances in GANs, pixels are definitely possible, and this has implications for all sorts of post-processing and all sorts of ISP-type filtering. We do see that geometry is much harder, but not impossible. So a huge place where deep learning techniques are still used today are in areas like maintaining 3D point clouds or maintaining dense representations of the world. There is a lot of work being done in this area from an academic point of view, but it is fair to say today that most of the state of the art of what's shipping, dealing with geometric techniques, is using classical techniques as well. And one other theme that's worth noting is parameterized systems are hard. So if I want to train something like a radial sharpening function, I could do that perfectly well for a given piece of the image, but learning a radial sharpening function which has got let's say the 3 or 4 lens parameters that I'm using, and learning a model that is portable across any type of lens and is parameterized in the correct way, that's something that is some progress has been made there, but it's still a very hard problem. So in many cases, parameterized systems have tended, and particularly ones to do with geometry, tend to use kind of classical features because there's a set of problems there that haven't been kind of solved in a very strong way yet by the community. Okay, so these are some of the common themes. Okay, I think I need to speed up a little bit, so these next couple of slides I'll try and advance a bit quicker through. So what will ship in 2017? So for and then kind of looking at what's the state of the art in theory versus what's shipping. Yeah, so the state of the art for object recognition is clearly deep techniques, but CNN type techniques will largely ship, but not exclusively. For object localization and for object descriptors, there's state of the art there is definitely deep learning techniques, but really there's a lot of classical techniques still shipping there, and it's going to be a bit of a mix. For optical flow, once again, there's great work in the literature, but virtually everything I know that is shipping today is going to use classical techniques. Similarly with feature extraction. With stereo, there's a mix in the state of the art and a mix in embedded, but the balance is a little different. And SLAM is largely classical and classical, certainly looking at a kind of HoloLens and looking at any number of other systems. It's largely classical techniques that are shipping. And then really quickly then to take a look at the gap. So why, when we have such good results in theory, does it take a little bit of time for people to implement them in practice? And there's a few normal reasons for that. Within deep learning, there's a few other reasons which make things a little bit harder. So in particular, there's kind of three key ingredients. You need data, you need good compute, and you need algorithms and expertise. And right now, for some large companies, this is an easy problem to solve, but for many other companies, achieving enough data, having an excellent type of compute silicon on your platform, and having algorithms and expertise, having talented deep learning engineers that can work on that data on that platform, this is a hard equation to solve right now. Yeah, it's getting easier, but today it's still a relatively hard problem to solve. So to look towards 2020, so one thing we should see is the gap is certainly going to shrink. It should be easier to take state-of-the-art techniques and deploy them quickly. So again, and quickly looking through each of the three kind of ingredient sections. For data, there's a lot of really interesting work done on unsupervised learning, particularly in the last kind of 9 months. There's a lot of work being done on the idea of kind of training a network to solve one problem that is easily composed as a unsupervised learning problem, and then using the results of that, using the feature embeddings that you learn in an unsupervised manner to apply them to other applications which themselves would be difficult to learn directly using unsupervised learning techniques. So there's the term there is kind of using pretext features. You solve one problem, you pretend you're solving one problem, you learn feature embeddings, and these kind of pretext type features you then apply to other problems. Also kind of open data sets, generative networks, and reinforcement learning. Each one of those things could take a lot of time to talk about, but certainly those trends will mean that data will still be a problem, particularly in automotive and cases where there is, where you need a lot of deeply domain-specific knowledge that can't be learned via unsupervised learning. But for general things like object detection or working on video, certainly I would expect open data sets and unsupervised learning by this time to be good enough that there isn't the same hard dependency as there is today. Compute, I'm pretty sure when the exhibition hall space opens, there's going to be any number of vendors and companies in there offering different new paradigms for compute for deep learning that can achieve higher throughput and lower power. So I think it's safe to say by 2020 we'll be facing a much richer set of options there for deep learning compute, both in terms of throughput and power. And also there's, one would expect the programming models that exist today for deep learning, there's a lot of options out there. One would expect there will be some consolidation of those techniques over time, and the deep learning paradigms that will dominate in 3 years' time, one would hope that there will be fewer of them, and they should have improved flexibility versus the set of tools we're using today. Lastly, algorithms and expertise. Yeah, like deep learning has been a very hot topic for kind of 2 to 3 years now, whereas it takes 5 years to do a PhD in something. So we would expect there to be many, many more deep learning PhDs on the market for hiring by 2019, 2020, and there'll be a lot more of the kind of the commodity techniques will become common knowledge as well. Okay. So progress we expect to see. Based on state-of-the-art research today, this is a set of problems that are very close to being solved. So some of them are already solved, some of them are just very, very close, or there may be kind of 1 or 2 papers published that are quite hard to implement, and one would expect more application-focused papers being published in these areas. So certainly anything to do with optical flow, stereo cost, temporal noise filtering, 3A for ISP, EKF for SLAM, general purpose super resolution. There's really good domain-specific super resolution being published today, but having a more general purpose version of that. And camera auto-calibration is also something we believe should be addressable in this sort of time frame. And then even apart from just making things we do today better tomorrow, there will be any number of new applications and algorithm types that aren't feasible today and will be feasible using deep learning techniques. Probably 2 things I'd call out there as a highlight. One is reinforcement learning for better context learned on device, and I think there's 1 or 2 talks on this on the technical track today and tomorrow. Another kind of big trend we would hope to see in the coming years is improved use of memory in deep learning structures and better temporal algorithms. So today, the way in which time or time-based information gets encoded is still a little crude. Like we have LSTMs, but there's definitely scope for a new paradigm to emerge there that will be much more powerful in how memory is used in deep learning algorithms. And that's an area I'd expect to see a lot of progress on that will enable a lot of new types of use cases. Okay, hardware problems. I'll skim through this really quickly. Fully deep learning-based ISP, full 3D reconstruction. Safety-critical applications are still hard to articulate exactly how a deep learning network is used in some cases. So there are barriers there to deep learning adoption. And then there'll be a bunch of things that are just harder to displace or good enough that will not be disappearing. So certainly there's so much invested in kind of compression. Even though deep learning is showing better results in many, many cases, it's safe to say that we'll still be using a lot of the classical techniques in 3 years' time because of technical inertia reasons. Okay, so key takeaways. One is that there'll be, well, it's pretty straightforward to say there's going to be better knowledge in 3 years' time than there will be today, and better programming paradigms. But one of the more interesting things to think is that as we are able to develop better algorithms for deep learning, this will create more demand for deep learning compute, which will create more deep learning algorithms getting deployed, which will in turn create more demand for compute. And in particular, one of the things I think may well happen is that there'll be an inversion of today's status quo. So today, if you pick up a piece of silicon and you try to use, and if you're an embedded engineer that's thinking about algorithms, you'll say, well, I know deep learning is going to be better for this problem, but really, I can really only, if I want to meet the real-time constraints I have to use a classical solution here because the classical solution will run that much faster than the deep learning version. It's easy to imagine a world in 3 years' time where, thanks to a lot of progress that's being made on deep learning compute acceleration, that we may well have, maybe not an order of magnitude, but maybe somewhere near there, that we may well have much more compute available that we can deploy if we're using a deep learning technique. So therefore, in 3 years' time, it's easy for me to imagine that if an algorithm engineer sits down, they'll say, well, I have this many DSP cycles available to me, but I have that many deep learning cycles available, which in turn will encourage more people to deploy deep techniques when they go to algorithm design. So that's definitely something we think would happen. And then, yeah, there's going to be very rapid progress in algorithms in general. So to wrap up, I would say that there's certainly one of the things that Jeff Dean is fond of saying in his kind of TensorFlow, whenever he gives a presentation on TensorFlow, is that if you're not using deep learning for a problem today, you probably should be. I'd go one step further than that, which would be if in 3 years' time, which is that in 3 years' time, if you're not using deep learning for a problem today, you probably will be in 3 years' time, because it's going to dominate many more application verticals much more quicker than you might originally think based on a quick inspection. Okay, thank you.
We've got time for one super quick question. I just saw, what would you see any?
Okay, sure. Question is, what % of computer vision deep learning cost is in algorithms versus data collection, data labeling? That's like what's the cost of acquiring it or licensing a data set versus staffing up a team of engineers type question. It's hard to give a direct answer. Like certainly data acquisition budgets can run into the millions of dollars for some people. Today though, I would say that to my knowledge, people are spending more money on talent than on direct data set licensing. Because to a certain extent, if you can hire the right people who are super good at using like synthetic data techniques, using generative data techniques, that would be where I would advise people to spend their money, rather than necessarily on licensing data sets, because you can potentially get a higher return there. For sure, you're going to need to spend some money on data too, but arguably, if you can get the right talent, money spent on talent would potentially be a better return. Yeah.
Great, thanks Cormac, we're out of time.